In this video, I will demonstrate how to find zeros of a polynomial function and discuss their multiplicity. Again, this is all working up to being able to graph a polynomial function using what we know about the degree, the leading coefficient, and the end behavior. So now we're going to get more components of what the graph would look like. We know that key points on the graph of any function are the x and y intercepts. Recall that the x-intercepts are ordered pairs R0 such that R is a real number solution of the equation f of x equals 0. The solutions R are also called the roots or zeros of the function. An easy way to think of this is that the zeros of a function are the values that make the function 0. That is, they are the input values that give us an output of 0. An important property related to polynomial functions relates to the zeros of that function. If a polynomial function has degree n and r is a zero of the function, then the following statements are satisfied. There are n zeros of the function, including repetitions, and we've seen that before. Do you remember when we solved quadratic equations? The degree is 2. There were 2 solutions. A linear equation is degree 1. There were 1 solutions, except for some special cases. When we had polynomial equations, we saw that earlier with the degree 3. There were 3 solutions, and so on. So the degree n tells us the number of zeros of the function. R is a solution of the equation f of x equals 0. And a really important part is that if r is a 0, then x minus r is a factor of the function. And then the point r0 is an x-intercept of the graph of f of x. Here's an example. To find the zeros of the function f of x equals 2x cubed minus 16x squared plus 32x. I've drawn the graph for you because there's something I want to point out as soon as we talk about the zeros and see what they are. But, from looking at the graph, you should be able to know what the zeros are. This is a graph that crosses the x-axis at 0, 0. And has a point also at 4, 0. So just from looking at that, we know the zeros should be 0 and 4. Let's see it algebraically. So to find the zeros, we're going to solve the equation f of x equals 0. That gives us 2x cubed minus 16x squared plus 32x equals 0. There is a common factor of 2x. When we divide out by 2x, we are left with x squared minus 8x plus 16 equals 0. This trinomial, x squared minus 8x plus 16, factors as x minus 4 times x minus 4. Correct? The factors of 16, whose sum is 8, or really negative 8, would be negative 4 and negative 4. So when we set those factors to 0, we get 2x equals 0, or x minus 4 equals 0, or x minus 4 equals 0. Dividing by 2 gives us x equals 0, or we get 4 as a solution which repeats itself twice. Now honestly, you're not going to have to make that repetition when you write the solution set, but I just want to point out something about that. So the zeros of the function are 0 and 4. Notice that 0 just repeated once, but the 4 repeated twice. So we say that that 4 is a 0 of multiplicity 2. The 0 is a 0 of multiplicity 1. But here's an interesting thing. Notice what the graph, or how the graph behaves at those zeros. At the 0 of 0, the graph crosses the axis there. At the 0 of 4, notice that the graph bounces off, or we sometimes say it touches the axis and turns away. It's really kind of an interesting thing. It's so amazing to me that when we have an odd multiplicity, think about how the odd graphs are, right? They continue, right? They don't have any mirror images, so to speak. The graph isn't like just half above or half below the axis. It is from negative infinity to infinity, right? The domain and range. And so when we look at through this multiplicity of 1, the graph kind of behaves like y equals x or y equals x cubed. It's going to continue to go through that point. But when we have a multiplicity of 2, the graph at that 0 actually behaves kind of like x squared, right? It has that mirror image. It bounces back off and kind of looks like that parabolic shape. And so this next page will kind of summarize those facts. If r is a 0 of a polynomial function f of x, then r has multiplicity k if x minus r to the k is a factor of f of x. That is, the value r is a solution that repeats exactly k times. And the behavior of a graph at a 0 of multiplicity k, if we have odd multiplicity, if a 0 has an odd multiplicity, the graph will cross the x-axis at that 0, or at the point r0. If a 0 has an even multiplicity, then the graph will bounce off or touch the x-axis at that intercept r0. So that gives us a lot of information about the shape of a graph around those x-intercepts. In this example, we want to determine the zeros of each function and state its multiplicity. Describe how the graph behaves at this 0. So if we look at this, it's already in factored form. So we don't want to undo that factorization, right? We had to sometimes do some multiplication to figure out the degree and the leading coefficient. But when we're trying to find the zeros, we want it in factored form because we have to set that function equal to 0. So in this case, we have p of x equals 3x cubed times 2 minus x squared times x plus 1 squared. When we set that function equal to 0, we set each factor equal to 0 and solve. So we get 3x cubed equals 0, 2 minus x squared equals 0, or x plus 1 squared equals 0. Dividing by 3 in the first equation gives us x cubed equals 0. So we would say x equals 0. 2 minus x squared equals 0. Applying the square root property, we would get 2 minus x equals plus or minus the square root of 0, which is just 0. So if we add x to each side, we get 2 equals x. X plus 1 squared equals 0. We apply the square root property to just get x plus 1 equals 0, so x is negative 1. But we have to state their multiplicity. So 0 has a multiplicity of 3, right? Because that exponent attached to that factor was a 3. 2, there's a square factor on that, or square on that factor, so the multiplicity is a 2. The negative 1 comes from this x plus 1 squared, so it has a multiplicity of 2. So what we know about the graph is that through the 0, the graph will cross, because that is an odd multiplicity. So the graph should cross at 0, 0. Because 2 has an even multiplicity, the graph should touch at 2, 0. Negative 1 also has an even multiplicity, so the graph will touch at negative 1, 0. Now I've drawn the graph, and again, we're not at the point where we're going to graph it yet, but I've just done this so that you'll see that this information that you found does correspond correctly to the graph, because here are our zeros. At 0, at 2, and negative 1. Notice that at 0, 0, the graph is crossing the axis. At negative 1, the graph is bouncing off or touching. At 2, the graph is bouncing off or touching the x-axis there. Another example is p of x equals x to the 4th minus 5x squared plus 4. To find the zeros, we're going to set that polynomial x to the 4th minus 5x squared plus 4 equal to 0. We know that the degree is 4, so we should get 4 zeros, including repetitions. We're going to try to factor this trinomial. The factors of x to the 4th are x squared and x squared. The factors of 4, whose sum is negative 5, would be a negative 4 and negative 1. We can set those factors equal to 0, or we can factor those as a difference of squares even further. So either way is fine. We would get x squared equals 4. So x equals plus or minus the square root of 4, which is plus or minus 2. Or x squared equals 1 to get x equals plus or minus the square root of 1. So just to note, if you had done the factorization, x squared minus 4 is a difference of squares. X minus 2 times x plus 2. X squared minus 1 is also the difference of squares. X minus 1 times x plus 1, and set those equal to 0. You could have the 4 distinct factors that you then set equal to 0 to solve. But notice that we do get 4 distinct zeros. Our zeros are 2, negative 2, 1, and negative 1. When you have 4 distinct zeros and the degree is 4, they each have to have a multiplicity of 1. It's only when the number of zeros is actually less than the degree is when you have some repeated multiplicities. So each of these has multiplicity 1. And we can see that because each factor where those zeros came from is raised to the 1. And so what that would mean is that the graph has to cross the x-axis at each of those zeros. And we see at negative 2, the graph crosses the x-axis. At negative 1, the graph crosses the x-axis. At 1 and at 2, the graph crosses the x-axis.